So, today we will discuss immobilization of enzymes. Okay, so immobilization of enzymes. So what does this immobilization of enzymes mean? If we look at an enzyme catalyzed reaction, for example, we have this starch solution here. Okay, and we add amylase solution into it. So this is the reaction mixture. In this reaction mixture, the amylase molecules are free to move, and they randomly move in this reaction mixture, and substrate and amylase collide with each other. They make enzyme substrate complexes, and the enzymes convert substrate into the products. The product made is maltose. So after some time, as this reaction is completed, starch is converted into the product, into the maltose. And still, these free enzyme molecules are there in this product. Okay, so this is amylase here, and this is product, which is maltose. Okay, so this is how free enzymes catalyze a reaction. During immobilization, we restrict the free movement of these enzymes in a reaction mixture. How do we restrict their free movement in the reaction mixture? These enzymes can be entrapped or encapsulated in some other substances, or maybe they are adsorbed on the surfaces of other substances. In this case, For example, we have this maybe a polymer or sodium alginate, sodium alginate. This amylase enzyme is entrapped into it. Okay, so this is amylase enzyme entrapped in sodium alginate. Okay, and we have this starch solution. Now, enzyme molecules are not free to move in this reaction mixture. Instead, what happens? The starch molecules from outside, they move into this encapsulated enzyme or entrapped enzyme. As there is high concentration of starch molecules outside, so starch moves into this sodium alginate bead. This enzyme present inside converts starch into the product, and this product that moves out of it. Okay, so after this reaction has been completed, the starch has been converted into the product, which is maltose, and this entrapped enzyme or encapsulated enzyme in the sodium alginate is removed out of this product. Okay, so bead removed and can be reused again and again. If we have more starch solution, we can use it again and again. So that's difference in, so this is immobilized. Immobilized enzyme. So immobilization is restricting the free movement restricting the free movement of enzyme in a reaction mixture. Okay, so how do we do that? Method of immobilization of enzymes. There are many ways of immobilization of enzymes. One of the method is by use of sodium alginate. There are other ways of immobilizing the enzymes, but we have this sodium alginate, use of sodium alginate in our syllabus. So let's see, this is sodium alginate. The sodium alginate is a jelly-like substance. This is a clear substance that is prepared by heating a powdered sodium alginate after dissolving into the water. And this is, for example, an enzyme which has to be immobilized. Enzyme to be immobilized. Anything else can be immobilized, not only the enzymes, but yeast, algae, or other unicellular organisms can also be immobilized by this method. Okay, it could be yeast that is immobilized this way. Okay, so this enzyme is added into this sodium alginate, and this makes a mixture of sodium alginate and, for example, amylase enzyme. Maybe any other enzyme that you want to immobilize. Okay, so this is mixed well by a glass rod by rotating this. So mix well. Then this mixture is taken into a syringe.
सर एक और बार रिपीट कर दें, आपने क्या रखा है ब्लू कलर से जो आपने बनाया बीकर में?
This is glass rod, and by moving this glass rod, we mix the sodium alginate and the enzyme together. And then this mixture is taken into this syringe. Okay. So this is mixture of enzyme plus sodium alginate. This mixture is poured drop by drop into another solution known as calcium chloride. Okay. So when this mixture of sodium alginate and enzymes is poured into calcium chloride drop by drop, these beads of sodium alginate are made, which are hardened by calcium. So calcium from calcium chloride that diffuses into, and it replaces sodium from the sodium alginate, and the calcium is deposited in these beads, and these beads are hardened by this calcium. Okay. So then these beads are removed out of it. Beads removed from the calcium chloride solution. Washed with distilled water to remove any enzyme from the surface, and then ready to use. How we can use these use of these beads or immobilized enzyme. What we can do is we can support these beads in a large syringe. This is the large syringe. Which has a molecular filter used here. We put these beads into it. Okay, so these are beads with immobilized milase. If we pour starch solution into it, so this is starch solution poured into it. So this starch solution is filled into this large test tube and allowed slowly to move out of it. So what will happen? The starch will be broken down to maltose by these enzymes present in these beads, and this molecular filter will only allow maltose to come out of it, but not the starch molecule. So at the other end, the product which is collected will be free of any contamination of an enzyme or any substrate. So the product collected is maltose, which is free of contamination of enzyme. So enzyme is easily separated from the product, and you see it is it can be reused again and again. So if we look at the important, yes.
सर जहाँ पे आपने फिल्टर लिखा है वो हमारा मॉलिक्यूलर फिट
Yes, this is small filter that allows maltose to pass through it. So this may be known as molecular filter.
सर आप एक दफा ऊपर वाली स्लाइड दिखा सकते हैं प्लीज?
Where?
थैंक यू सर.
Okay, so let's see importance of immobilization of enzymes. As you have understood, immobilized enzymes can be reused. Okay. Then immobilized enzymes are thermostable and pH stable. And they can easily be separated from the reaction mixture or product. Okay. So obviously, if they can easily be separated from the reaction mixture, so in this case, there would be a low cost of separation of an enzyme from the product. So low cost of separation of enzyme from product. Okay. So how these enzymes are thermostable or pH stable? Immobilization makes enzymes thermostable or pH stable. You know, if this is, for example, an enzyme molecule.
सही वाटर एंजाइम का क्या मतलब है?
Sorry?
सही इमोबिलाइजेशन के बाद क्या लिखा हुआ है?
Makes enzymes.
ओ ठीक है, थैंक यू सर.
Makes enzymes thermostable or pH stable. So for example, if this is an enzyme molecule, it has been enlarged, and this is, you know, an alginate bead where this enzyme has been entrapped. This is an enzyme entrapped in sodium alginate. What happens? The sodium is replaced by the calcium. So calcium is deposited into this alginate bead. So this is calcium molecules, or calcium ion, sorry, deposited in this alginate. So calcium supports, you see, from outside there is crust-like structure made by the calcium. So calcium supports this structure from outside. Calcium supports structure of enzymes. So increasing temperature does not change the shape of enzyme. So enzymes can withstand higher temperature before denaturation. Okay, so very high temperature as compared to the free enzymes is needed to denature these enzymes. Similarly, the same happens if the pH of the medium is changed. So as they can withstand higher temperature, so the enzyme activity will be higher. You see, if free enzymes denature at 40 degrees Celsius, but for example, if an immobilized enzyme that denatures above 60 degrees Celsius, so we have flexibility to increase the temperature of the reaction medium uh, above 60 degrees Celsius. So free enzymes denature at 40, so the rate of enzyme activity will be lower in free enzymes. And as immobilized enzymes temperature could be raised to 60 degrees Celsius, so they would have higher rate of enzyme action as compared to the free enzymes. Hope you have understood it.
सर आप ऊपर वाली स्लाइड जी इधर ये दिखा दें नहीं इससे ऊपर जहाँ आपने इम्पोर्टेंस ऑफ इमोबिलाइजेशन लिखा हुआ है
सर आप ये सारे के स्क्रीनशॉट्स ग्रुप में भेज देंगे और वो कल जो प्रैक्टिकल किया था उसका डॉक्यूमेंट भी प्लीज भेज दें.
Okay. As now let's see. Researchers isolated a sucrase enzyme from the bacterium Bacillus subtilis. They immobilized the enzyme in alginate beads. The researchers investigated the effect of temperature on the activity of the immobilized sucrase compared with the activity of the same enzyme free in the solution. And they recorded their results on this graph. The rate of immobilized sucrase is given in this graph, and the sucrase free in the solution is given. So this is graph showing the rate of free sucrase enzyme, and this shows the rate of immobilized sucrase. The question is, with reference to figure 3.1, compare the effects of, you have to compare the effects of temperature on the activity of immobilized sucrase with activity of sucrase free in the solution. So when we compare, we should give, just give me a minute. Okay, so this is the question. With reference to figure 3.1, compare the effects of temperature on the activity of immobilized sucrase with the activity of sucrase free in the solution. So let's see, we have to compare these graphs. So maximum enzyme activity for both of these enzymes is the same. 100% enzyme activity is at this temperature. You can, put a line here with a ruler, a straight line with ruler. And this 60 degrees Celsius. At 60 is optimum temperature. So at 60 degrees Celsius, it is the max percentage enzyme activity. Same for both of the enzymes. Okay. At 40 degrees Celsius, it is the same as well. At 40 degrees Celsius, it is this much, around 77%, and it is also same. However, from 40 to 60, 40 degrees Celsius to 60 degrees Celsius, the percent activity of immobilized enzymes is immobilized sucrase activity is higher. Okay. And then from 60 to 65 degrees Celsius, 60 degrees Celsius to 65 degrees Celsius, there is decrease in the enzyme activity in both.
Sir?
Yes.
Sir,